Okay. So, hello to everyone. My name is Christian, and I am a PhD student at University of Zaragoza. And today I'm going to show you a bit of my work, especially about I'm going to talk about the biochar as a catalyst for pyrolysis vapours upgrading. First of all, I would like to introduce the different application of biochar, then how can be activated, and how can it be used to pyrolysis oil upgrading, and the conclusion, of course. So let's start with the biochar applications. So the biochar is produced from the slow pyrolysis of biomass, and the slow pyrolysis of biomass can generate two different products: the biochar, which is the solid phase, and pyrolysis vapors, which is a mixture of the permanent gases, water, and organic condensable fraction. But let's focus on the biochar, which is carbonous solid with an amorphic and aromatic structure. And it's very interesting, the application of biochar in different fields, because it's produced from a renewable precursor. It's relatively cheap and stable, and can be easily functionalized, and depending on the pyrolysis condition can contain interesting functional groups. And furthermore, the spent biochar can be disposed in soil, or can be gasified to produce CO. In this scheme, there are summarized all the application of the biochar, starting from the pollutant, the employment of biochar as pollutant removal or catalyst or energy storage. And however, all the biochar needs to undergo different processes before the employment in these fields. For example, my research is centered on the creation of a porous material, so I need to improve the surface area of the biochar, since the pristine biochar has almost 0 square meters per gram, so at 1 or 2 square meters per gram. So we have to activate the biochar, and we can do it in 2 different ways. One of that is the physical activation, and the other is the chemical activation. The physical activation consists in the partial gasification of the solid. It's a process which occurs at high temperature, around 500, 700 degrees C. It depends on the gasification agent, which can be or CO2, water, or oxygen. And as show it in the table, the surface areas that can be achieved are pretty high, and the extent of the gasification is evaluated with the burn-off degree, which is the relative difference in mass of the solid before and after the gasification. The higher is the burn-off, the higher is the gasification level, which means the higher is the surface area. The variables that have to take into account we need to consider when we perform an physical activation are activating time, temperature, pressure, and precursor usage. Why the precursor? Because depending on the pyrolysis condition, the biochar can be more or less reactive to gasification. For example, elevated high pyrolysis pressure can change the structure of the biochar from amorphous to crystalline, so the reactivity of the biochar can be reduced. Also the pyrolysis temperature, because if we increase the pyrolysis temperature, we can promote the secondary char reaction, which are essentially the cracking. Is a char produced by the cracking reaction of the pyrolysis vapors. And this secondary char is less reactive than the primary char. And finally, also the pyrolysis atmosphere can affect the reactivity of the biochar, since, for example, at CO2 atmosphere during pyrolysis can create some groups on the surface of biochar which can help the gasification. So, in order to study the influence of the precursor, the pyrolysis condition, we have my group, we have carried out an experiment and different experiments producing 11 biochar under different conditions, under different pyrolysis conditions, and following a 2K full factorial design with 3 factors, which are temperature, pressure, and CO2 percentage in the pyrolysis atmosphere. So we took all these biochars and we have activated them under the same conditions with CO2 at 800 degrees C and 0.1 megapascal for 60 minutes. We took the activated biochars and we have analyzed, we have characterized them in terms of surface area and PSD, pore size distribution, and the results we have analyzed the results with Minitab, which is a statistical software. And in order to identify the factors which have an influence on a significant influence on the output variables to into account. In this case, for example, we can take a look to the normal photo standardized effect, and we can see that the red dots means that the factor is significant for that variable, and the blue dot means that it's not significant. As we can see, for the volume of micropores, the only significant value is the only significant variable is the temperature, which means that biochar produced at lowest temperature, once activated, gives us the highest volume of micropores. On the other side, mesopores are not influenced at all by the factors to take into account, and the VAT and total volume of mesopores, total volume of pores, sorry, are influenced by the temperature as well. And in the case of the volume of total pores, also it was also identified interaction between the 3 factors. So we can conclude that in order to obtain high an activated carbon with high surface area, a high level of micropores, it is important to use a biochar with the lowest temperature, a low temperature. This in our case 400 degrees. Moving on, the influence of the activation time. We try different activation time: 15 minutes, 30 minutes, and 40 minutes for a biochar produced at 500 degrees C and 0.1 megapascal. And in the table are reported all the results in terms of textural properties, so VAT, total volume micropores, mesopores, and so on. BC, as I previously said, is the biochar non-activated. So as you can see, the SBAT is very low; it's 1.68. And for the different activated biochar at different activating time, we can see that there is an increase of the surface area for a maximum at the PSC 40. And you can see that we can create through the activation of CO2 micropore structure with almost 83% of micropores. About the temperature and pressure, the influence of temperature and pressure in physical activation processes, we have tried to follow the same design of the study of the precursors. And we have done a 2K full factor design with, in this case, the factors equal to 2, which are the temperature and the pressure. And again, we have defined in this time a variable alpha, as reported here in the formula. And we can see that in the case of the VAT and the alpha total volume of pores, you can see that the only factor which influences these variables was the pressure and an interaction between pressure and temperature. Meanwhile, the temperature itself has no influence at all. On the other side, the alpha of meso and alpha of micropores are independent from the factors took into account. This means that if we look again at these plots, we can activate the biochar at the lowest level of temperature in this range. This means 700 degrees C and the highest pressure in order to obtain the highest surface area and highest volume of pores. So on the other side, we have the chemical activation. In this case, we obtain the activation, so the gasification of the solid with the help of a chemical agent. And we have two different kind of chemical activation. The first one starts from the biomass itself. So the biomass is impregnated with an aqueous solution of a chemical agent. Then it's dried and filtered. And finally, the impregnated biomass is pyrolyzed. The other route involves the first step, which is the pyrolysis of the biomass, and then the impregnation of the biomass, and so on, ending with a final heating treatment of the biochar, of the impregnated biochar. These two routes have advantages and disadvantages. One of that is, for example, the biomass. With biomass, the impregnation step, it's more effective since the biomass is not hydrophobic, such as just as biochar. But on the other side, with biochar, we can have a more flexible process, since we can buy the biochar from a company who produce it, and we can activate it depending on our necessities. An important factors for the chemical activation is the impregnation ratio, which is the ratio between the mass of agent in solution and the mass of biochar. And the operating condition that has to take into account are the procedure, which are one of the two, temperature, pressure, and the agent usage. If we look at the agent usage, we can see that there are different, and depending on which on the agent, the activation temperature is different. And the most used one is the KOH, but it's a corrosive material, just as sodium hydroxide. So it's hard to handle with it. So other agents are zinc, the ZnCl2 and phosphoric acid, which can create pollution problems when the spent biochar has to be disposed, because it's not so easy to separate the biochar from the phosphorus, for example. And finally, we have the K2SO3, that is the one that I'm using actually, because it's easy to handle, it's not toxic, it's not corrosive. So the activating procedure is not well understood yet, but these are the reactions which can be involved in the activating procedure. And so in order to study the effects of the impregnation ratio and pressure, we have done again the same study with 2K factor design. In this case, the two factors were the impregnation ratio, 1:1, 2:1, and 3:1, and the activating pressure. We kept the temperature constant at 700 degrees C in order to avoid leaching of metallic potassium with the gases flow. In this case, we can see that both factors had significant effect on the surface area, on the ATA value, but the most significant one was the impregnation ratio, which the higher the impregnation ratio, the higher is the surface area obtained. On the other side, the pressure seemed to hinder the gasification, so we obtain a surface area low value of surface area in this case. About about the Porsa distribution, it seems to be no influence at all by the factors taken into account in the study. So now we can move to the employment of biochar as catalyst. As I've already said, I'm producing porous material, but I'm producing them in order to use the activated biochar as catalyst or catalyst support. The process that I'm studying is the upgrading of the pyrolysis vapours. This because I consider pyrolysis oil the mixture of water and the organic condensable fraction, which this mixture can be used in further processes depending on the pyrolysis conditions. But in general, they lower the yield of biochar and of the permanent gases. They can condensate inside the system, causing clogs and systems breakdown. And the higher water content, around 75% for slow pyrolysis, can decrease the heating value of the bio oil. So in order to improve the quality of the system, we need to upgrade these vapours through cracking, dry reforming, and steam reforming. And usually the catalysts used, commercially used, are the zeolites, are noble metals supported by zeolites. But we would like to study the suitability of biochar, activated biochar as catalyst, because it's cheaper, it's relatively cheap, and it has a high specific surface area. And the ashes, the content of inorganics, can improve the gasification and freeing the surface from coke deposition. And what else? Not working, I'm sorry. Okay. I would like to say that the condensable fraction of the bio oil, it's a mixture of more than 100 compounds. So the study, it's very hard. So for our work, we choose a mixture of model compounds, which are eugenol ethanol as compounds derived from the lignin decomposition, and acetone and acetic acid from the composition of cellulose and hemicellulose. And we have added like 50% in weight of water. The performances were evaluated through the definition of the total yield, defined as the total mass of gas produced divided by the liquid fat in dry basis, and the selectivity defined as the millimole of the gas divided by the dry liquid fat. We have used a fixed bed reactor with a condensation train and a micro GC to analyze the composition of the outlet stream of gases. And the first test we carried out was a cracking test. And we tested different biochars and activated biochars. BC is a non-activated biochar, and PAC 15, 30, and 40 are the activated biochar at a different activation time, and CAC is the chemical activated biochar. As you can see, the best result was obtained for the activated biochar, the physical activated biochar with the highest extent of gasification, so the one obtained after 40 minutes of activation. On the right plot, you can see the H2 production in terms of millimole per minute, and the area and the activation rate of the gray one, which is the active PAC 40, is so it's the best catalyst. It can be related to its surface area and the volume of micropores, because the PAC had the highest surface area and the highest volume of micropores. Then we used this catalyst to test steam reforming test. So we have added the 50% of water in the model mixture. And we have changed the gas hourly space velocity of the liquid, of the gas, and the temperature of the forming. And the results are shown in these two plots. The gas hourly space velocity was, for the gas hourly space velocity was identified a maximum at 400 for 1400,500 hour -1. And about the temperature, we can see that the temperature has a positive effect on the conversion, and the highest conversion was obtained in the case of the highest temperature, with a molar ratio between hydrogen and CO of around 4. So now we try to simulate a pyrolysis atmosphere. So we just added 3 different ratio of CO2, 10 kilopascal, 20 kilopascal, and 30 kilopascal, in order to promote the dry reforming to lower the H2 to CO molar ratio. And also in this case, we found an optimum with a CO2 partial pressure equal to 20 kilopascal. And you can also see that the deactivation, which is the red line, is slower than the one obtained in steam reforming. So the CO2 can help the regeneration of the biochar surface. Finally, we have tried to we have seen that for the model mixture, the biochar was working okay, but we also tried a real bio-oil recovered from the slow pyrolysis of the production of the biochar, and we obtained a better result, which means that was a yield of 140%. It can be that it's above the 100% because we are considering the liquid in dry basis, so we are not considering the water content. And we can see that we obtain 140% of yield, which is possible because of the higher water content in the bio-oil, which was 75% instead of 50% in the model mixture, and also because the presence of lighter compounds. And as you can see from the right plot, we can see that the activation is slower, sorry. So we can conclude that biochar can be used as catalyst for the upgrading of pyrolysis bio-oil. So in order to conclude this presentation, we can see that the biochar is a versatile material that can be used in different fields. The activation procedure which can be divided in physical and chemicals, are needed in order to employ the biochar. And in physical activation, the operating temperature in the studied range does not seem to affect the resulting activated biochar textural properties. And in chemical activation, the pressure and the impregnation ratio only affect the value of the resulting surface area and not the pore size distribution. And at the end, the activated biochar can be used as a sustainable alternative in catalysis or as catalyst in pyrolysis upgrading processes. So I would like to acknowledge the European Union for funding my research and the World Green Carbon project. So thank you, and if you have any questions.